Thanks. Well, it's certainly good to be here. I'm certainly in the pro-snow camp. Everything I'm going to talk about, this is joint work with Tobias, Barthel, Natàlia Castellana, and Krause. So let's start out with some notation and terminology. So throughout the majority of this talk, T is going to denote a rigidly, compactly generated tensor triangulated category. So this is a tensor triangulated category. It's compactly generated as a triangulated category, and significantly, the compact objects coincide with the dualizable objects. So in particular, the unit for the tensor is a compact object. And so I'm going to denote also the internal hom using square brackets. Okay, so we have a lot of the usual suspects: derived category of a commutative ring, derived category of an E-infinity ring spectrum, stable module category of a finite group, G equivariant spectra for a compact Lie group G, motivic stable homotopy category over a characteristic zero field. These are all rigidly compactly generated categories. Okay? So if you have such a thing, sitting inside it, you have the subcategory of compact objects, which I've just told you in these examples coincide with the subcategory of dualizable objects. Okay? So this category sitting inside T is an essentially small, rigid tensor triangulated category. So rigid just meaning that every object is dualizable. Okay, so by construction, we're considering the objects that are dualizable. So it's a rigid tensor triangulated category, and there's this whole story that was mentioned in the last talk about how we can then classify the thick tensor ideals of this category using the Balmer spectrum. Okay, so we have the Balmer spectrum of this essentially small rigid tensor triangulated category. It comes equipped with the universal theory of support for compact objects, and this universal theory of support classifies the thick ideals of this category. Right? However, as was also mentioned last talk, we care about non-compact objects. Some of the most interesting objects in these categories are not compact. So we really also want to understand the non-compact objects in T. We want to understand the big category. Can we classify those objects? Can we classify the localizing ideals of the big category T? And one way we go about trying to do this is by constructing some kind of theory of support for arbitrary, not necessarily compact objects in T, right? Unfortunately, constructing notions of support for not necessarily compact objects is a bit of a subtle thing to try to do. For example, there's the warning that there exist commutative rings R such that no theory of support for the derived category of R can satisfy both of the following two properties. First one is, let's say, the tensor product property. Saying that the support of the tensor product of two objects is equal to the intersection of the supports of those two objects. And the second condition is what I call the detection property, which is saying that if the support of an object is empty, then the object is zero. Okay? There exist commutative rings R such that the derived category of R has non-trivial tensor nilpotent objects, and you can easily check as a little exercise that in that case, you can't have a theory of support with both of these two properties. And so what it's telling us is that there's really no hope of having a general theory of support that has all the properties that we might want. There's some real fundamental limitations to what we can achieve. Okay?
How weird is this ring, R?
It's like showed up in the last talk, like a truncated infinite polynomial ring. It's a non-Noetherian ring. But nevertheless, we can still see what we can do, and I'd like to discuss the Balmer-Favi theory of support that was talked about in last lecture, but I would like to kind of just quickly say some of the same stuff again so we get it back into our mind and we have the kind of notation that I want to use. So let's just quickly recall the business about finite localizations. So if Y is a Thomason subset of the Balmer spectrum of compact objects, well, this corresponds to a certain thick ideal of compact objects. By the classification of thick ideals. And this in turn corresponds to a compactly generated localizing ideal. This is a compactly generated localizing ideal of the big category. Okay? And there exists a smashing Gauss-field localization gamma yt t lyt whose acyclic objects, or in other words co-local objects, are this compactly generated localizing ideal. Okay. It's a smashing localization, so really the localization is just tensoring with the localization of the unit, and similarly the co-localization is just tensoring with the co-localization of the unit. Okay. It's a smashing localization. And I'd like to use the notation EY for this co-localization of the unit, and FY for the localization of the unit. Okay, and so basically since it's smashing, you really just need to consider the kind of localization sequence for the unit object, which is an exact triangle that takes the form EY, unit, FY, suspension VY. Okay, so to any Thomason subset of the Balmer spectrum of compact objects, there's an associated finite localization of the big category. Okay? And so we can use these to define the Balmer-Favi theory of support, and as in last lecture, we're going to assume that this space is weakly Noetherian and what that meant is that for any point P in the space, you can find two Thomason subsets y1 and y2 such that singleton set is y1 intersected with y2. So in other words, you have your point P, you can find a Thomason subset y1 and a Thomason subset y2 such that you can kind of isolate that point using them. Okay? And then you can define the object GP to be EY1 tensored with FY2. And this object is not dependent up to isomorphism on the choice of Y1 and Y2, and we can consider the functor of tensoring with this object. Right? Tensoring with this object is doing two things. First, you're tensoring with Fy2, which is performing the finite localization associated to Y2. That amounts to restricting to the complement of Y2. And then you're tensoring with EY1, which is doing the finite co-localization associated to Y1, which amounts to restricting to Y1. So tensoring with GP amounts to doing a localization followed by co-localization. Okay? Okay, so we could then define, we could then define the stalk at P to be the image of this functor. And then we could define the Balmer-Favi notion of support for any object T in our big category. The support of T is the collection of P such that this is non-zero. Okay, so this is a theory of support for the objects of T, which is lying in the Balmer spectrum of compact objects. This is the Balmer-Favi theory of support. You can prove a couple of little things about it, just maybe to help get us some intuition about this theory of support. So, for example, if you apply it to a compact object, it recovers the universal support for compact objects. If you apply it to the co-localization of the unit, you get Y. If you apply it to the localization of the unit, you get the complement. And maybe I'll also mention, if you take the support of this object GP, you just get the singleton P. So, oh yeah, maybe another thing is that you take the support of the tensor product of two objects. This is always contained in the intersection with equality in some circumstances. So, for example, if S is compact, or one of these objects EY, or one of these objects FY. So, sort of, for sometimes, you know, if one of these objects is one of these particular things, then you have this sort of equality, but in general, you don't. So the tensor product property does not necessarily always hold. And so you can then define, we say that T is stratified if we get a bijection from the localizing ideals of T to the subsets of this space. Okay, so maybe more precisely, we say T is stratified if this is a bijection. Okay. And as mentioned in the previous talk, one can prove that T is stratified if and only if two conditions hold. The first one is the local to global principle, LGP, which says that for all objects T is contained in the localizing ideal generated by GP tensor T for P running over all the points in the support of T. So it's sort of like T can be built from its stalks. And then the second condition was the thing called minimality, And this said that for all points P, the stalk is a minimal localizing ideal of T. Okay, can people read that? Right, and so the intuition for the last point is just that under this sort of map, the stalk at P maps to just the singleton P, subset P. And this is an inclusion-preserving map, and so if you have this localizing ideal which is getting mapped just to the singleton point, in order for this thing to be an injection, certainly that localizing ideal cannot contain anything, any non-trivial localizing ideals, because on the right-hand side it doesn't. Okay, and so these properties, this is coming from the work of Benson, Iyengar, and Krause, and also Hausdorff, Balmer, and Strickland, kind of isolating kind of these two properties as really the heart of what's going on. And so, a couple more things to say about that. Okay, so a couple of things to remark is that, well, it follows just from the definition of the local to global principle that it implies the detection property for support. Right, if you have an object T whose support is empty, then that right-hand side, that localizing ideal is 0, so T is 0. So the local to global principle implies the detection property for support. The other thing is that we can prove that the local to global principle holds if the space is Noetherian. But it doesn't hold in general, right? And so this is what Scott's talk was all about, was sort of getting a deeper understanding of exactly when does the local to global principle hold, but it does hold if the spectrum is Noetherian, for example. Okay, and then the other thing maybe I want to mention here is just that if the category is stratified, that implies that the tensor product property holds for support. Okay, and so what we get from this is that we can't expect every category to be stratified, right? If a category is stratified, then it has the detection property and also the tensor product property. I mentioned that we have derived categories of rings for which that is inconsistent. Okay, so we certainly can't expect every category to be stratified, but what you can prove is you can prove that this theory of support, with some sort of quotes, is in some sense the best choice for a support theory that has any chance of classifying the localizing ideals. And so I could be more precise about that, but basically, if you have a space which is weakly Noetherian, and you have a theory of support for the objects of T in that weakly Noetherian space, which induces a bijection between the localizing ideals of T and the subsets of your space, in a way that's consistent with the usual classification of thick ideals of compact objects, then your space is this Balmer spectrum and your support is this support. So I could, you can write it, you can be precise about it, but in some sense, this is sort of the only choice. And that allows us to really define, as I have, stratification as a property of a category, right? There's no sort of auxiliary choice of support theory to consider. If any support theory is going to do it, this one's going to do it, so we're going to define stratification using this support theory. Okay, so it's a property of a category. Okay.
Do you have such a result without the weakly Noetherian?
So I think the answer is yes, right? It's not true.
For stratification.
Yeah. Well, okay, so we can talk about it. It's you need to be a bit more careful about what you mean on the right-hand side here, because this map is not surjective. Then we can talk about it. Okay. So it's a property of your category. If your category is stratified, then you get this sort of classification of the objects of your category up to this kind of weak notion of equivalence described in terms of the localizing ideals that the objects of your category generate. Okay? But that's not the only kind of equivalence you could consider on the objects of your category, right? When you're classifying localizing ideals, what you're really doing is you're looking at the objects that you can generate kind of using the tensor triangulated structure and arbitrary coproducts. I mean, you could choose other things. You could consider the objects that you can generate kind of using the tensor triangulated structure and arbitrary products, for example. You know, there's other choices one could make. And so I'm just trying to say that classifying localizing ideals is not like some God-given universal thing, you know? There are other things one could try. For example, classifying co-localizing subcategories or co-localizing coideals. So let's define what they are. Coideal of T is a co-localizing subcategory of T, so it's a fixed subcategory closed under products, which is a coideal in the sense that if you take the internal Hom into it, so it's sort of closed under taking the internal Hom of an arbitrary object into it. This is what I mean by a coideal. Okay? And so, for example, if your category T is monogenic, meaning that it's just generated by the unit object, then you might be familiar with the fact that in that case, every localizing subcategory is automatically a localizing ideal. That if the category is generated by the unit, then localizing ideals and localizing tensor ideals are the same thing. Same thing is true here. So if T is monogenic, then co-localizing coideals and co-localizing subcategories are exactly the same thing. Okay. But another source of examples is, well, if E is any collection of objects, in T, then, well, the left orthogonal of this collection of objects, so those objects T such that Tu is 0 for all U in E, this is a localizing ideal. And the right orthogonal those T such that Ut is 0. This is a co-localizing coideal. So co-localizing coideals turn up in this kind of natural way. And we can then define cosupport So we can then define cosupport. So again, let's assume that our space is weakly Noetherian, same hypothesis as before. And for any object T, define its cosupport be those points such that if you take the internal hom into T from GP, you get non-vanishing. So you can make this definition, and you could define the co-stalk at P to be the image of this functor homming out of GP. Okay. And you could say that T is co-stratified if this notion of cosupport gives you a classification of the co-localizing coideals of T. Okay, so this notion of cosupport can potentially classify the co-localizing coideals, and you can prove analogous theorems to like what we had before. You can prove that T is co-stratified if and only if two conditions hold. One would be what I would call the co-local to global principle, saying that every object is contained in the co-localizing coideal. Co-localizing coideal generated by its co-stalks, and co-minimality condition that for all P, the co-stalk is a co-minimal, a minimal co-localizing coideal. Okay?
That's presumably a theorem, which should be.
It's a theorem. Well, it's based on ideas of Benson, Iyengar, and Krause, but then I guess we prove it in this setting. And so then another point to make is that, again, sort of the co-local to global principle implies the co-detection property. So the co-detection property is saying that if an object is non-zero, its co-support is non-empty. Okay, so the co-support detects non-triviality of objects. And that again follows just from what I've written on the board there. Okay, so one can do this, and then one can prove a theorem analogous to what I said for support, basically that this definition of co-support is sort of the only possible choice that has a chance of classifying the co-localizing coideals. You can give a kind of uniqueness statement about this theory of co-support. Okay. So that's all well and good, but
what about those two properties? So you addressed the first.
I'll say more about that.
After you erase it.
More about that, not right now.
So, did you just say that co-stratifying ability is a property?
Yeah, yeah. Because of this kind of uniqueness result. Okay, so let's check the time. Okay, so I don't know how we're going, but basically one of my goals in this talk is I would like to make the somewhat bold claim that co-support, as defined up there, is unavoidable. that even if you don't care about co-localizing coideals, there's a chance that co-support might come up in your life. I mean, it might not, but it might. And it's a bit of a bold claim, so co-support is unavoidable. Okay. And when I was preparing this talk, I think I counted 5 potential small forms of evidence towards this bold claim. You may not buy all of them or any of them, but sprinkled in this talk, explicitly and implicitly, there are 5 potential justifications for this claim. So let's just sort of keep it in the back of our minds as we continue our discussion of co-support and see if I convince you at all.
Are you going to tell us what those 5 are? Or not?
Yeah, some of them. Yeah.
So in everything is very symmetric, except there was a kind of localizing, like you could localize a category over a subset of the Balmer spectrum
Yeah.
using this. But here, is there a localizing, kind of, can you localize with respect to, because there's like a cohomological localization.
All right, so I mean, I think that maybe both of these supports, okay, I guess I'm not quite sure what you mean. I mean, there's certainly a question, but I'm not sure how I can interpret it in several ways.
Yeah, it wasn't very clear.
Yeah, so...
Like, could you cohomologically localize, at least when it's co-stratified? That's the question. Does the cohomological localization exist? With respect
I'm
to
not sure what you mean. I mean, you can always localize your categories whether or not they're stratified or co-stratified, so I might be misunderstanding you. What do you ask? Can you ask it again at the end? And
okay.
Maybe it'll kind of be clarified.
I guess maybe the question was that, like, this is question of whether cohomological localization exists in general, for instance, for spaces.
Oh, you mean like existence of Gaussian localizations?
Yeah, but in spectrum, is it true?
Okay, so yeah, this is very much tied up with those questions. And okay, let me just say one thing. So for example, I mentioned there's a bunch of properties a category can have, right? A category can be stratified. You can have the local to global principle. You can have the detection property. Right? And this implies that, and that implies that. And we can also talk about whether or not the category is co-stratified, and the co-local to global principle, and the co-detection property. That implies that, and that implies that. Now what you can prove, without too much necessarily trouble, is that this implies that, implies that, implies that. So that in some sense, co-stratification is harder than stratification, and one possible intuition for why that's the case is, again, because sort of proving that homological localization exists is harder than proving that homological localization, whatever it's the right thing to say, right? But if your category is co-stratified, then they all exist, yes. Every co-localizing or localizing thing is strictly co-localizing or like localizing, they all exist, yeah.
I mean, the cohomological localization shouldn't really be relevant here. I mean, you've got the internal hom from your EV, and that's a Bausfield localization.
Yes.
And I think that's the only Bausfield localization you need for this story, isn't it?
Yes, but I guess it's more the question of whether or not a given kind of co-localizing subcategory is the image of a Bausfield localization, like that question. Okay, so I'm sort of getting a bit sidetracked, but I'd say that this is sort of the part of the story that is perhaps not surprising if someone is kind of thinking about these things. But what I would say is something surprising that we discovered is that these 3 properties are all equivalent. So that actually the co-detection property implies the local to global property principle, and that implies the co-local to global principle. So in fact, this story simplifies to where you have the detection property, you have the local to global principle, or if you prefer, the co-detection property. You have stratification, and you have co-stratification, and you have implications like this. Okay? And so this is one example of this, because what it's telling you is that even if you are just interested in localizing ideals, local to global principle, the stuff that Scott was talking about, that's actually deeply tied up with whether or not co-support detects anything. So cosupport turns up. Okay. So another aspect of the story that's interesting is that there's an interesting relationship between cosupport and support. I heard some noises that reminded me. So there's a relationship between support and cosupport. So that if you take the cosupport of the internal HOM of two objects, that is contained in the support of the first object intersected with the cosupport of the second object. Okay. And this is an equality. Sometimes it's an equality, for example, if your first object A is compact or one of these EYs or FYs. So there are some circumstances where it's equality, but in general you just have this inclusion. And what I think is a quite significant discovery due to Benson, Iyengar, and Krause is the discovery that the statement that this is an equality for all objects is actually equivalent to the category being stratified. So T is stratified if and only if this is an equality for all objects.
So that's the core of the tensor product property.
Yes, it's sort of analogous to the tensor product property, although it's sort of subtle because it's mixing the support and the cosupport. And so this is a really interesting theorem because it's telling you again that even if you have no interest in co-localizing coideals, even if you're only interested in classifying localizing ideals, if you're interested in stratification, the question of whether or not you can do that is intimately related to the behavior of cosupport. So again, cosupport is unavoidable. Another example of an interesting part of the story is that cosupport is related to the Tate construction and it reflects the topology of the Balmer spectrum. And so there are different statements one could make, but let me just make this the simplest, cleanest statement. So let's assume that T has the co-detection property. Then the following are equivalent for a Thomason subset Y. The first is that the cosupport of EY is contained in Y. And recall that the support of EY is Y. So this is saying that the cosupport of this object is contained in its support. And the second condition is that Y is both open and closed, and we have a decomposition of the spectrum in this way. It's a disconnection of the spectrum. Okay? And so, I think I'm running out of too much time to give a proof of this, but one could give a proof of this given what we have seen so far. And I think this is a very interesting result because it's telling you that even if you don't care about localizing subcategories, even if you only care about the compact objects and you want to classify them and you want to understand the Balmer spectrum, understanding the topology of the Balmer spectrum is reflected in the behavior of cosupport. So again, even if you only care about the compact objects, cosupport shows up. However, what I would say is that from what I've presented so far, I'd say that there's still a real something that's really missing. I mean, I think that I've sort of defined this notion of cosupport, and I've said some things about it, but I think it's really quite conceptually unclear where in the world it comes from. You know, I defined it in terms of taking the internal hom out of this object GP. Why? Why do that? Sorry?
Completion.
Completion, yes, but why? But like, really why? And so what I would like to do in the remainder of the talk is sort of give a, try to give an explanation for sort of where co-support comes from. Okay? So the birth of co-support, if you like. And so, I mean, to do that, let's consider our original category T. And we can consider T-op. And well, T-op inherits a triangulated structure. It's a triangulated category. And, well, I mean, the thick subcategories of T are just the exact same thing as the thick subcategories of T-op. I mean, they're just the same. Now, recognizing that coproducts and products get flipped, you know, when you take the opposite category, you would then have that localizing subcategories of T. Those are exactly the co-localizing subcategories of T-op. And so from this perspective, you know, in terms of thinking about localizing and co-localizing subcategories, it feels like really it should just be something that's happening in T and something that's happening in T-op. But when you bring the tensor into the game and you start talking about localizing ideals and co-localizing coideals, it's not a priori at all obvious how this thing here could handle that. Okay, so for example, T-op, it inherits a symmetric monoidal structure, but it's not necessarily a closed symmetric monoidal structure. There's not necessarily any internal hom. And also it's a, you know, it has a tensor, but I mean, for example, tensoring with a given object does not necessarily preserve coproducts anymore. So I might call this a non-closed tensor triangulated category just to emphasize those sort of potential deficits of it. Okay? So, nevertheless, sitting inside T is our subcategory of compact objects, and now I'm going to write TD for it because it's really the fact that they're dualizable that is relevant now. And this is a rigid category. Spanier-Whitehead duality gives an equivalence between TD and its opposite. So we have a tensor triangulated equivalence from TD to TD-op. Okay, and this is T-op D sitting inside T-op, and this is sitting inside T. So this is an equivalence of tensor triangulated categories. These have exactly the same thick tensor ideals, exactly the same Balmer spectrum, exactly the same universal support. And so really, I think the way to think about it is that really T and T-op are two tensor triangulated categories that share the same subcategory of dualizable objects. Okay? And in particular, the Balmer spectrum of this is the same in both cases. Okay, and so what I would claim is that what we're really doing is, I would claim, again, you don't have to believe my claims, you don't have to accept them. I would claim that we're not really classifying localizing ideals of T, rather we are classifying localizing TD submodules of T. So let me define that, explain it. So let me explain that cryptic remark. So a localizing TD submodule of T is a localizing subcategory such that TD tensored with L is contained with L. So it's closed under tensor with dualizable objects. Now it just turns out that if T is rigidly compactly generated, then this is the same thing as a localizing ideal. Why? Well, because this condition here is like a little lemma. Saying that this is the case is equivalent to saying that loc, the localizing subcategory generated by TD tensor L is contained in L, and T is generated by dualizable objects. This is T. So saying that you're closed under tensor by TD is equivalent to saying you're closed under T. So in a rigidly compactly generated category, the localizing TD submodules are exactly the localizing ideals. What if we consider T op though? So on the other hand, a localizing TD submodule of T op, what is it? It's a localizing subcategory of T op, in other words, a co-localizing subcategory of T. Co-localizing subcategory C of T such that TD tensored with C is contained in C. But we can give a little argument that, well, saying that TD tensor C, tensoring something with a dualizable object is the same thing as taking the internal hum of the dual of that thing. So this is equivalent to saying that the internal hum of TD into C is contained in C. And same business, that's the same as saying that loc of TD C is contained in C. That's saying that T C is contained in C. Okay, so a localizing TD submodule of T op is exactly the same thing as a co-localizing co-ideal of T. Okay, so this is the perspective that allows us to unify these, what's going on here. And so I'm running out of time, but let me just try to just quickly say some remarks about what I would like to say. So, the opposite category T op is never compactly generated. Okay? T is, a compactly generated category. T op never is. But it's perfectly generated. It's perfectly generated by the Brown combinates duals of the compact objects in the original category. And perfectly generated triangulated categories satisfy Brown representability and so on. And so what one can do is sort of take a perfectly generated non-closed tensor triangulated category and prove that, and construct a Balmer-Favi style of support. One needs to be a little careful about how one does that because the way it's done traditionally is using these finite localizations, which are depending on compactness and everything, but one can sort of do a game that uses the perfect generation to construct a Balmer-Favi type support, which when you apply it to T, you recover the usual thing, but when you apply it to T op, you get the co-support. So I don't really have time to explain it, but the bottom line is that this co-support is really just the support in T op. And the unifying thing is that this notion of support one defines in this more general setting really is a support for classifying the localizing TD submodules of your category. And you just specify it. You just sort of, in the case of a nice category T, is classifying the localizing ideals. In the opposite category is classifying the co-localizing co-ideals.
What is this general setup?
The general setup would be C is a perfectly generated, non-closed tensor triangulated category. And you would take a Thompson subset of dualizable objects. And you prove that the localizing subcategory generated by the dualizable objects supported on Y, tensored with T, this is you prove that this is perfectly generated. And that's, it's not completely obvious. I mean, it's using really the fact that these are dualizable. And you then have a Balmer localization, whose asequence are these. And in the case where you do it in a nice category T, this just gives you the usual finite localization. But if you do it in T op, this becomes, you check, this becomes...
Yeah, no, I was just asking about the setup. So you have a triangulated category tensor, but you don't assume internal harms and compatibility to co-products.
Yeah.
It's perfectly generated, and what's the relation between the perfect and the dualizable is the relation there?
I don't think any relation is necessary.
Perfectly.
It's just perfectly generated.
That's the setup.
Yeah.
And when you plug the usual story, you get the usual story. When you plug the opposite category, you get a cool story.
Yeah.
So that's 4.
Yeah, that's 4. 5 is the original uniqueness theorem for classifying colocalizing coideals. If you want to classify colocalizing coideals, you have cosupport.
4.5.
Okay, anyway, I'll stop there.